first speaker this afternoon is Joel Jaeggli. Joel has been a NANOG participant since the late 1990s. He's worked in various networking adjacent jobs, starting with Timeshare and Unix Tech support, Linux and Unix system administration, and at network equipment vendors. Not to mention online gaming, and most recently, he's been involved in the deployment of content delivery networks. Joel Jaeggli has worked for Fastly since 2014 and is currently a principal network architect. Welcome back to the NANOG stage, Joel.
Thanks a lot. I have a lav, so I guess I'm hot and I don't need to stand directly in front of the podium. Yeah, so I thought I would just plunge right into this. So this is a thing that some of you have no doubt experienced. Which is that you get up in the morning, you go to work, you jump on Slack, and immediately you're eyes deep in an incident. Yeah, so my colleague Justin Odom says to me, we shouldn't be seeing SSH land on any of the systems from a non-bastion, right? Definitely not. Okay, now we have a problem. Yeah, so that brings me to my introduction. This is an experience, comes in two parts. One of these is a recreation of the incident, and the other is a philosophical exploration of why we have this kind of incident and why it remains relevant to the networking community at large. So to recreate this experience, and this is, I don't know, 2 years now, we got failed login attempts to hosts that should be protected by an ACL. So there is a lot of network forwarding plane protection associated with these hosts. This packet flow should not exist. We start to look at it immediately, revisiting our syslog. Pushes the timeline for the incident back by about a day. So apparently we didn't catch this quite as fast as we would have liked. But direct SSH connection attempts to hosts from non-bastion server IPs have been observed. No successful connections have been observed. This affected hosts in only 2 sites, and ACL rules in all sites were verified as applied in reviewing the actual switch ACLs. So within an hour of declaring an incident for this, the problem was no longer apparent. All the switches were functioning as normal, and all we had done in order to do that was reapply the ACLs. So the observed problem, therefore, is mitigated, but what happened and why? And so takes 30 plus days to figure this out. If we look back a couple more years, I think this is about 2008. This is a letter from one of our vendors, and it's a case where egress ACLs were not applied in an FPGA, like ultimately in a case where they should have been because queries were running against the FPGA at the same time. So there's a race condition. The application of this ACL failed. The ACL claims to be written. You can inspect the FPGA all you want, and it's still not there. But this is not an FPGA. This is just a Broadcom ASIC. So we started inspecting the individual ASICs directly. So we're essentially diffing the contents of the TCAM against what should be applied from the control plane. And we hardwire this into our metrics exporter. So we don't know what causes this issue now, but we can now detect it. And one of the things that happens is as soon as we start looking for this issue, it starts to appear all the time. That's an interesting problem. So when it occurs, we reapply ACLs. And yet, you know, we end up with lines that mysteriously appear and disappear in our ACL that simply don't get programmed. All the counters are working. Thing is still dropping packets as it should be, but some rules are not taking place. The vendor had actually already identified this particular problem in at least one other case. And their answer is simultaneous reads and writes to TCAM operations may update TCAM hardware tables. Again, there is a case where if you perform a read before a write is complete, these don't get applied. And the workaround to that is to restart the agent, which for those of you familiar with these sorts of platforms, means your line card reboots, which is a visible outage to a whole bunch of people. So that's not so cool. One of the other workarounds, as it turns out, is actually simply to rewrite the ACL again. And that happens to be like a lot less hitful. But the question is, okay, now that we've written this detector, why do we see this issue all the time? Did we only get really lucky and we only saw this because of that attacker who managed to exploit this? And the answer is no, we created the issue. So when we wired that diff into our metrics collector, we ran this command every 5 minutes instead of once an hour. The likelihood of you causing the race condition increased dramatically. As it turns out, if you run this on platforms with more ASICs, you can cause it faster. So when you have the switch platform with 12 line cards as opposed to the 1 RU top of rack switch, you can basically cause this to happen like once a day if you just keep continuously writing the ACL in there. And the question I have for like people who run platforms like this is, like we ran this platform for like 5 years before we first detected it. How could it go so long without us finding it? And there's a couple of postulates to this. Those of you who have the same platform, you're very reluctant upgraders. In our case, these things tend to have uptimes measured in years. And we will update them in the event of emergency vulnerabilities in our platforms, but it's very unlikely that we would do this on a whim. Somebody else had to have tripped over this before us. And we can suppose maybe that the sequence of events that made this possible got more frequent at some point. And that could be our behavior. So for example, rewriting our ACL more frequently, or in the specific case, writing a detector that was much, much faster. And as soon as we did that, of course, we damaged the viability of our platform, so we had to figure that out. But we still have the question of how do we interrogate that the configuration that is applied to our switch platforms is correct? We actually scrape the control plane hourly to ensure that no one has manually typed changes into our devices, that our configuration is still applied, that the agents that are running on the system haven't done something that they shouldn't. But the question is, are they? Superficially, without interrogating every single ASIC in the box, all of these boxes had fully applied ACLs at all times. So previous incidents did demonstrate cases where the forwarding plane no longer matches its configured state. So we have metrics and alerts and countings and counters that should be incrementing, and in many cases they do, and yet the rules still aren't applied. This is a case of the control plane being unable to interrogate the state of the ASIC properly or to restore it. And I think there's a number of things that play into this. One of them is we don't like it when routers spontaneously reboot. We find that to be extremely uncomfortable, and when they do it, like, we open attack cases constantly. So I think there is a design brief in our industry around having these platforms be stable to the point where they operate in a way that is like visibly correct all the time. You know, if you have ASICs that spontaneously reboot due to parity errors, for example, you're swapping out line cards. So we did all of these things. We have change management. We have CI performed unit tests. We have peer review. We have programmatic application of rules, including dry runs. We test for error conditions when we apply rules, and we roll back in the event of failures. We monitor applied configuration for changes. We have metrics showing rule matches, our increment encounters. We do regular port and vulnerability scans. We have a separate compliance team and independent auditors. And the thing that caught this is a vast army of malicious actors who might not be very creative, but they are persistent. One of the problems with interrogating whether your ACL is correctly applied is vantage point. So if every ASIC in a box save one has the rules correctly applied, the vantage point that you use to inspect your ACLs or check your forwarding path may not be the one that the attacker is going to use. One of the things I said, little Easter egg, in that incident discussion, there were 2 pops. Yet, you would have to be extremely lucky to have 2 ASICs in different routers in different parts of the world fail in the same way at the same time. So in fact, we weren't that lucky. But what we do have is tunnels. So we were getting login failures in the second pop because packets that passed through the ACL in the first pop matched a rule bound for an IP address that were simply shipped to another pop for compliance reasons. Those packets passed through the same SSH blocking ACL basically because they matched an earlier rule. So because we allowed the tunnel, because the source IP is known to the other pop, it's one of our IPs, the tunnel packets ended up in a second pop. So that's a case where the ACL is correctly implied, but what your forwarding path is doing is not what you think it is because you have shuffled the bits around yourself. Yeah, so that was a real fun one. Yeah, so that's a case of solve problem immediately, spend a month figuring out what the actual problem is, and now spend the better part of 2 years considering what good praxis for this would actually look like. So here we go. Part 2. Want to think about why switches and routers are the way they are and why this kind of problem comes up. Because if you have this problem on your Linux box, you go look at IP tables and you're like, hey, there's a rule missing. If your kernel is doing something weird, you like bust out strace or BPF or eBPF and you watch packets flow. And this means that failures in your Linux box are relatively transparent. But then we get these 2 big 20th century impulses. And these are the things that make our business possible. Scalability through parallelism and centralization, order, and control. And so I get to pick 2 of my heroes here. We got Jean Amdahl and Mikhail Foucault. Very different disciplines. So those of you who are history majors or political scientists will relate to one of these characters more than the other. But I think they both have very useful insights that are related to each other. So Amdahl came up with what's called the universal scaling law. And it's sort of less popular than Moore's law, but I think in many respects, it's more relevant to us all the time because Moore's law, has problems with complexity. And what the universal scaling law says is that the overall performance improvement that can be gained by optimizing a single part of a system is limited by the fraction of the time that the improved part is actually used. And so packet forwarding has this super cool property, which is that if you make packet forwarding more scalable by having 2 packet forwarders rather than 1, as long as they don't have to relate to each other. So for example, you're doing flow caching, you get 100% speed up immediately, right? So our infrastructure fundamentally leverages that in a number of ways. We get faster ASICs, we get simpler forwarding, we get more ASICs, then we get functional blocks inside ASICs that do forwarding. We get a whole bunch of really important insights from that. The other part of that, the Foucault bit, is we take and we separate the logic which constructs our forwarding plane and the forwarding plane itself. ASICs, like white blood cells in the body, are really just space aliens. They don't actually know anything about IP packets. They just know about bits. They match on bits. They move cells from input buffers to egress ports. They are pieces of sand that are bashing electrons together. And we got super smart at building these things. And so we've taken these nice control plane abstractions that we have, these routing protocols, and we have made very specific instructions for what a device is supposed to do with a packet. So the other thing that happened is, in order to get faster, they became less like generalized computers, and they became more opaque and simpler. Yeah. We have a control plane which ingests configuration topology, signaling from network adjacencies, external controllers. We salt that with a healthy dose of predefined logic, semi-opaque system defaults from our vendors, and our operator expectations, and then we dispatch that into a forwarding plane. These ASICs, content addressable memories, FPGAs, and weirder devices, they hopefully spend a lot of time forwarding and very little time being programmed. If you have billions of packets per second flying through a device, the amount of time that it spends being programmed or verifying that it is correct versus forwarding is enormously small. And these become very hard to simulate. So our Linux packet forwarding path, we can interrogate. These things, not so much. You don't go out and simulate several dozen ASICs with 10 billion transistors as part of your virtualization environment. Very easy to virtualize your network control plane, build a fake topology, have dozens of routers, make OSPF flow, add IP ACLs, and so on. Simulating the hardware, much harder. And then we come up with new conventions. So software-defined networking is what happens when you drop the fiction that the RIB and the FIB assembled by the software stack are the basis for programming the forwarding plane. So instead of consulting our routing table, we just whack a bunch of rules in there. And those rules come from some kind of upper layer abstraction that turns business logic into forwarding instructions for these devices. So it could be policy-based routing. It could be IP ACLs. It could be primitives that we've had for a long period of time. So URPF, remote triggered black hole filtering. Many people who've been here long enough have destroyed their forwarding path with BGP flow spec. MPLS, segment routing. These are all ways to match bits in some header and execute specific instructions before them. So if we back up a little bit, in 1970, like a nice positive futuristic view of what a router would look like is the thing on the left. And because network people are extremely boring, it immediately turned into the device on the right. So imagine trying to sell beige metal boxes on the basis of how cool they look. Yeah, nobody wants to own the MIT Lincoln Labs imp, except for the Computer History Museum, which is where that particular one is. What happened since then? Well, the boxes didn't get any prettier. But what we thought might happen would be 2 decades of innovation. We'd all be wearing silver body stockings. We would have IPv6 and extension headers. And the internet would be operating on some kind of upper layer abstraction, like the locator identity split, because we incorrectly concluded that routers wouldn't scale with Moore's law. Now, of course, there's an interesting property to that is they don't have to, because we could do parallelism because the actual operation that we need to perform is very simple. But what actually happened was we got inconsistent but ruthless simplification of expectations. So some people believe things should work some ways. How they actually work is a little bit different from that. But what they did was they got really, really fast. So in the last 20 years, that scale of performance has increased by a factor of 1,000 or more, which is not the normal sort of scaling factor you see in an industry. But the downside is these devices aren't very flexible, but they are still extremely stupid. So yeah, that box in 1986 is a lot closer to the IMP in the sense that it has a general purpose processor on it. By 1998, you have a really interesting crux, a place where this system diverges. And so you got a 7200 VXR there, sort of the last vestige of software forwarding in Cisco 7000 series devices. The same year you have the Juniper M40 and the Cisco GSR. For our industry, one of the things you'll notice if you read the Cisco GSR introduction press release, no mention of Ethernet anywhere. None at all. That VXR, on the other hand, came with like 2 Ethernet ports on the front. So clearly, software forwarding, the future. You know, when you look at what's happened to us since, in 2017, I had that box on the left. It can forward about 5 billion packets per second. You know, that is, well, let me rephrase that. That box could forward about 5 terabits per second. The box in the middle can forward about 100 terabits per second, and the box on the right can forward about 25 terabits per second in a 4U that only draws 300 watts, right? So things got wild and they got real small. You went from having networks of these fixed function ASICs to having a bunch of processors on an ASIC to having networks of fixed function ASICs on an ASIC. So we're at the point now where single chip boxes that we have all our instructions programmed in are doing 100 terabits per second in one ASIC. We took all this peace dividend that we receive from being able to mess with the forwarding plane, and we did smart things with dumb hardware. So one of the things that I got really interested in that finally led to me going to work for Fastly in 2014 was static hash distribution functions. And this was because I hated load balancers. The load balancer was a stateful device that was in the middle of my network at all times. It was implementing ACLs to protect servers, and it was distributing incoming requests, sometimes fairly, but mostly unfairly, and at incredible expense. So we got rid of it. We have an Ethernet switch. We can do hashing. We had early implementations of resilient hash functions, and we salted those with our own software. And this resulted in us spending a lot of time bashing on the forwarding plane of these Ethernet switches. Super fun. Also a really good way to misprogram your Ethernet switch, which is why this has happened to me more than once. These devices also have a limited amount of TCAM space, but if you use all of that to write ACLs, one of the things that happens is any packet that you can drop it at effectively the capacity of the incoming network. So if you have 10 terabits per second worth of bandwidth into a POP, you can drop 10 terabits per second worth of packets. This is super relevant when you run a CDN because people like to DOS you. So you can do policy-based routing. And one of the things that we did that a lot of people have done since then is build source port mappings to hosts. And the upshot of this is we didn't have a load balancer for incoming traffic. We didn't have a NAT box for outgoing traffic. So you give a POP a prefix, you give each cache or server a pool of source ports, and now they all use the same IPs. None of them are individually addressable, and everything is cool. Some of these things are referred to as SDN functions, but the SDN mindset implies putting the simplest possible set of instructions that achieves your aim in the forwarding plane. So it doesn't really matter what they are. You have a business objective that you come to this with. If you are a traditional network operator, obviously that business objective is forwarding packets on behalf of your customers. So that's a relatively straightforward one, and a bunch of tools exist to support you in doing that. If you're banging on bits in some other way because you're very server-centric or application-centric, the switch and the network ASICs themselves don't support those kinds of abstractions. So you end up with some kind of controller that implements your will here. When these things fail, there may be very little that's externally observable other than errant forwarding. And this is a persistent complaint that I have with network operators is I have more visibility because I send packets over their network frequently than they do, right? I send more packets than they do, and I can find the ports in their backplanes and their routers that are generating errors faster than their NOC can. So yeah, that's fun and exciting, but I have a more basic visibility problem, which is that I have this very well instrumented application, and I can tell sometimes when my routers are wrong, but I'm convinced that I can't tell all the time. And that's a really interesting problem for compliance, for security, for performance, and other questions, because sometimes these things are not visible even to me. And the primitives that we're using here can be thought of as a long list of match action rules and no more. And almost all of the primitives that we're going to operate over in the future are us adding some abstraction so that we can describe some bit that we want to match somewhere in a header and carry out specific instructions over. And people have built their lives and careers on that. Yeah. So you may never be able to entirely trust the forwarding plane is programmed the way you think it is. These boxes, despite all of the telemetry and all the effort we've done with them are too black to peer into. So I don't have good answers for this, but it is a thing that I have spent years at this point working on. So I thought I would share it with you. Thank you.